Welcome back to Geometry, Chapter 7, Section 3. In this book, but you don't have to have this book to learn this concept, we're talking about moving things around on a piece of graph paper, and today we're going to do ones that rotate. Rotational transformations is what they're called. So, here I've got a blue flag, and I got a point P. And I'm going to rotate that blue flag around to where the red flag is. The blue flag is the pre-image, the red flag is the image. How you can describe this is thinking about if there were strings tied to the top of the blue flag and the bottom of the blue flag, and they go and they're under a push pin that's at point P. Then as we rotate them around, then the angle that this back string would rotate to the back string of the red flag is 60 degrees. The front string would also rotate the same amount, but it'd go right there 60 degrees. So every part of the flag rotates 60 degrees and stops no further. So how we describe this is because it went that way, it went the way a clock goes, it is called clockwise, abbreviated CW. It can also go the other way. We could have started with the red flag and we could rotate it back to the blue flag, and then it would go counterclockwise. It would go the opposite way that a clock goes, counterclockwise. My papa and granny used to have this weird clock that ran backwards, and it was all, but you could look at it and figure out the time. And my husband used to have a watch that was Bizarro Superman that did the same thing. I think he gave it to my son Josh. But anyway, if y'all have ever seen one of those backwards clocks, they go counterclockwise. They're clocks, they go counter. So that's how you describe it. How many degrees you're rotating it and in which direction. Pretty easy, right? Okay, so here are 3 different ways things can be rotated around a point. This one is where my blue baton is getting rotated to the red baton, and they're not in a straight line with the string that goes down to my point P. Okay, so they are called non-collinear. They're not in a straight line, and we're rotating from Q R to Q prime R prime, from blue to red. It gets rotated around to its new place, and it would be a certain number of degrees that X got rotated, and we went clockwise because we went from blue to red. Okay, here, this is in a straight line. Pretend, if you want to see it real straight, look in the book. It's in a straight line with our point P, with our piece of string. And we have QR going over to Q prime R prime, X number of degrees, and this one is also clockwise, but it's just swinging from here over to there. It's swinging around there. This one, the one end of it is nailed down. It's under the push pin. So R and R prime is the same thing as point P. They're all right there together, and just the Q got rotated around from Q to Q prime. R and R prime are the same point, and really kind of so is P if that's where our push pin is. Does that make sense? Read it in your book if it doesn't. Alright, here is another thing we do with these transformations. One is, we're doing it on graph paper, and of course you would use real graph paper and a ruler and make it look good. But my first figure down here is the blue one. And it's this little kite looking thing, A, B, C, D. And it's getting rotated around the origin, that's where my push pin is, at 0, 0. And it's being rotated 45 degrees. So if you look at A, it got moved around 45 degrees. B got moved 45. C, 45. D, all of them got moved 45 degrees. If you look at the coordinates of each of these points, A is at 2, -2, B is at 4, 1, C is at 5, 1, and D is at 5, -1. Once you get over here to the image, A prime is at 2, 2, B prime is at -1, 4, C prime is at -1, 5, and D prime is 1, 5. Do you notice anything about those? Take a look. Look again. If you notice that you're switching what's written in A and B, so like These two, 2 and 2, you can't see it. But this was 4, 1, and this is 1, 4. This is 5, 1, that's 1, 5. Not look at the negatives and positives. 5, 1, it's 1, 5. And then if you look at the negatives and positives, the y's, what they were when they were over here, when they went over here, they switched. Negative 2 became 2, 1 became negative 1, 1 became negative 1, and negative 1 became 1. So what happened is it switched, x and y switched, and y became negative. And that's one way they will describe transformations, and they'll make you fill in. Well, if you switch it and you make this one negative, what would the points be? So on the test, they have these where you have to figure out what the points are by them telling you this way of what's going on, because there's patterns in this that we find. Okay, here's another one. Here we're going to take this blue baton AB and we're going to flip it over line K and make A prime B prime, and then we're going to flip it again, whoop, over line M and make B double prime A double prime. Remember I told you if you do it again you can have double prime. Okay, and if you look at this, flip, flip, it is the same thing if we had taken a string and attached it to B and put a push pin at P and attached a B string there and rotated it around. That makes the same thing as if we rotation. So it turns out that you can rotate something or reflect it and then reflect it again, and they end up being the same. You can flip it twice or rotate it once. It's the same thing. It also turns out that if this angle right here is x, the amount that you rotated it, the whole thing around here, is 2x. So it rotates 2 times x is the same thing as flipping it twice. I like flipping it twice better. Rotations sometimes confuse me a little bit. And you will find that some of you are more natural at this than others. If you're really good at spatial relations and seeing things in your head, and manipulating them, this is very easy for you. One of my kids is very artistic, and he just did this great. Where sometimes I have to go, huh? Where he never has to do that. He can just do it. All right, so my angle BPB prime is 2x. It's double that x. If x equaled 60, what would angle BPB, that should be B double prime, B double prime equal? It would be 120, because 2 times 60 is 120. Your book does it again, making these triangles. So there's a triangle, and it gets flipped over the line, and then it goes like this. And then it gets flipped that way, and it looks like that. And they said this was 60, so what's all that? It's 120. But really, whether it's a triangle or a baton, same thing. All right, now this is back to where I told you, remember when you were a baby, you have to think way back, and you had those block puzzles where it was a little cutout shape and a wooden backing, and you slide it over and chunk, you can put the puzzle piece into the puzzle. If I still have it, I would bring it up and show it to you. But my kids haven't been babies for a real long time, so I'm not sure what those puzzles are. All right, so that is, if you could take that puzzle piece and rotate it around and it clicked into itself before it gets back up top again, that's it having rotational symmetry. So that's what we're doing here, rotational symmetry. I should have written it down. So here is my block. It's got a push pin in the middle, and this is the top where the red line is. And I can rotate it. If I rotated it to go here, that would be 45 degrees. If I rotate it here, that would be 90 degrees. So if that far, imagine it turning on the push pin, you turn it 45, turn it all the way where this side's on that side, it's called 90 degrees. So can these shapes have rotational symmetry where they would click back into themselves? Okay, so our first one is this octagon. If I turned it, would it click into itself? Yes, it'd go click, 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 click. So it would click into itself 4 places. It'd click into itself at 45 degrees, 90 degrees, 135, and 180. So think about it. Click, 45, click, 90, click, 135, click, all the way around 180. How about the parallelogram? It would only click in one place. If I went all the way around, turning it upside down, click, it would go into itself. So does it have rotational symmetry? Yes, but only in one place. How about that trapezoid? Nope. You would have to turn it all the way around for it to click back in, and that's not having rotational symmetry. It's got to click somewhere else. This is used a lot in graphic design. As humans, we find symmetry in shapes appealing. So if you end up going to art college and going to graphic design, you would do a lot with this sort of stuff we're doing this chapter. All right, math is great. See you next time.